continue to study lecture 4, part 1. And then if we have more time, we continue to study lecture 4, part 2. Okay. And I guess some of you are doing the lab, right? Yeah. Yeah, and Mr. Hill, with the lab engineers, will guide you to do the lab experiment. We have two lab lessons. The first one is synchronous machine, and the second one is induction machine, typically for induction motor. Okay, so remember, uh, take into account the lab schedule, the lab timetable, and you need to attend the class and pass the lab session. Okay, before we take the final exams of this course. Sorry, I get sick. Okay, so last week we discussed about the equivalent circuit of induction motors. Yeah. So now we review a little bit. Okay. So we have induction motor, right? Yeah. We have stator and rotor. Okay. Yeah. So for induction motors, we have two kinds of rotors. The first one is wood rotor, right? And the second one is squirrel cage rotor. Yeah. So if we use wood rotors, we should have rotor winding. Yeah. We should have slip rings and brushes. So if we use squirrel cage rotors, we have rotor bar, right? Or we say rotor conduction bar. Yeah, we have shock ring. We have two shock rings. Okay, and of course for stator, we should have stator winding. Yeah. Okay. Yeah. So according to the construction of induction motors, we have some important parameters. Okay, so here we have stator winding. Here we have rotor, right? So we have many important parameters. Okay, so normally for stator winding we use a strip 1 or we use S. So for the rotor side we use a strip 2 or R. R mean rotor, S mean stator. Okay, so at the stator windings we have R1, right, or RS. This is stator resistance. We have X1 or XS. We have I1, right? This is complex numbers. We have V1. This is phase voltage. Yeah. What else? We have Z1. This is stator impedance is equal to R1 plus JX1. Yeah. So because we consider the induction motor, so the output will be the mechanical power, right? Mechanical power, and the input is a P in, and this a electrical power. Okay. Yeah. So we need to calculate B1, Q1, S1. So if three phase, we have three-phase our input power. Yeah. For the rotors, we have RR, XR, ZR. Okay, this is rotor resistance, rotor reactance, and rotor impedance. Okay, we also have IR. This is rotor current. Okay, yeah. And remember, we have many kind of speed. Right. So continue. Now we talk about speed. Yeah. So at the induction motors, we have synchronous speed. Synchronous speed. That means and since is 60 FSE over B. Okay. Yeah. Sometimes we say synchronous speed or we say stator speed. Okay. And the next one we have rotor speed. Rotor speed A and R, or sometimes we say NM. Okay. Yeah. Or sometimes we say N rotor, right? Yeah. And we have another space we say is slip it. This is NS, and NS equal to N since minus N and R. Okay. Yeah. So we also have another concept. It is S slip, right? Slip. So SE N sin minus NR over N sin. Okay. Yeah. So for, according to this formula, we can get NR, right? So here we get N sin times S equal to N sin minus NR. Okay. Yeah. So we modify a little bit. You can get NR. Okay. You move NR to the left side, and the N sin times S move to the right side. So you get NR E N sin 1 minus S. Okay, we also discuss this formula, right? Yeah. Yeah. So remember that we can calculate rotor speed by these formulas. Okay. So remember rotor speed. So sometimes we say mechanical speed. So mechanical speed. Yeah. Okay. So for here we can modify these formulas. So if I don't want to use the speed, I can use angular speed. Okay. So if I use angular speed, we have omega r. Okay. E omega sin 1 minus s. Okay. Yeah. Because we consider induction motor, so we should make sure N are different and sin. Okay. Yeah, by using the slip s. Okay. N R uh, never equals to N sin synchronous speed. Okay. Yeah. So you should remember this one when we consider the operation of induction motors. Okay. Now we consider the frequency, right? Frequencies. We have different kinds of frequencies of induction motors. The first one is stator, right? Stator electrical frequencies. We say FSA. we have rotor electrical, right? Yeah, frequencies. We say F, R, E, and we have rotor mechanical frequencies. We say FR. Okay, yeah, and uh, yeah, we also studied before. We have the relationship between FSE and FRE, right? So we have FRE is equal to S times FSE. So we have FR is 1 minus S times FSE. Okay, yeah, so remember that. Okay, so we already reviewed some knowledge from last week. Now we come back to the lectures. Okay, so okay, one more. Yeah, so last week we also discussed the equivalent circuit, right? Of induction motors, right? So for the stator side of induction motors, we have R1, yeah, we have JX1, then we have what? We have RC. This is rotor. Sorry, this is reluctance, right? And we have JXM. This is magnetization reactance. Okay, so here, yeah, so this one is the V1 or V phase, and this one is I1, right? Yeah, and here we have E1. The E1 means internal voltage. Okay, so here, yeah, we have E ER 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 means the rotor internal voltage, right? Yeah. And then we have RR, okay, and then JXR like this, like this. Okay, so this one is a stator, right? Stator circuit. This one is rotor circuit. Okay, but you should remember we isolate the stator and the rotor. Okay, it's not good. We need to combine stator circuit and rotor circuit into the same equivalent circuit. Okay, so later on we will consider it. So now we continue with rotor circuit. Okay, we have rotor internal voltage, RR means rotor resistance, XI mean rotor reactance, and we also have current, IR, right? Okay, so if we pick up this circuit, okay, and analyze, okay, we have this light. Okay, so yeah, so for this light, yeah, we for this line we have ER, right? We have RR and JXR. Yeah, this one is rotor uh, equivalent circuit. Okay, and we also have IR, right? IR. Yeah. So now we consider the operation of the rotor. Okay, for the rotors we have two operation modes. The first one is that the rotor is locked, right? So if the rotor is locked, that means rotor speed is 0. So if rotor speed is 0, the slip must be 1, right? Right. And if the rotors rotate, okay, so n are different from 0, so s will be different from 0, and we have the limit of s is higher than or equal to 0 and less than or equal to 1. Okay, yeah. um, so we have two operation modes of the rotors. Okay, the rotor is locked or the rotor is rotating. Okay. Then if we apply Kirchhoff 2 for this circuit, we apply Kirchhoff 2 for this circuit. So we have ER is RR plus JXR, okay, times IR, right? Or we can get the IR is ER over by RR plus J. Okay, plus JXR. Okay, and resistance we don't have for complex number. Okay, here it is. Here it is. Okay, yeah. And if the rotor is locked, the induction motors operate as transformer, right? Yeah, operates as transformers if the rotor is locked. Okay. Yeah. So for we have ER becomes EI0. 0 means the rotor is locked. Okay. Yeah. And if we say we have ER is S times EI0, so in this case, that's correct because S is 1. S is 1, so we have ER is EI0, okay, and XR is XR0. Because induction motor operates as a transformer, so FS is equal to FRA, okay, because S is 1. So now come back here. Yeah. So we have the comparison between the two cases. The rotor is locked. That means the stationary rotors. And the second one, rotor is rotating. Okay. Yeah. So we need to compare. Yeah, so if rotor is unlocked, induction motor operates as transformer, right? Transformers. Okay, so for the transformers, we have primary winding and we have secondary windings. Okay, so here we have I1. Yeah, we have the number of turns at the primary winding N1. Okay, we have V1, we have S1, B1, Q1, and F1. This is the frequencies of the primary winding. So for the secondary windings, we have I2, right? What else? Yeah, we have I2, we have V2, we have B2, R2, X2, and yeah, so on. Okay. Yeah, and we have F1, sorry, F2. F2 mean the frequencies of the secondary winding. Okay, so for this transformer theory, we have F1 must be equal to F2, right? Right. Yeah, this is the transformer theory. And now, if the rotors is locked, right? So IM is similar to the operation of transformer. So now for the rotor, yeah, for the maybe I draw another way. Okay. So now we have stator winding, stator winding of induction motors. A A overcomer, B B overcomers, C overcomer. This is stator. And we have rotor like this. Okay, we have A, B, C. So for induction motors, we have FSA, right? FSA mean the stator electric uh, uh, frequencies, the electrical frequency, and for the rotor we have FRE, right? Yeah. So remember that the rotors is locked. That means S is 1. So we follow the transformer theory, we can make sure FSE, AFRE, okay? And we have the formula before, we have FRE is S times FSE, and then the rotors is locked, so S is 1. So that is the reason we have FRE is equal to FSE, okay? Yeah, 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 similar. So now I demonstrate to you why if the rotors is locked, we have FSE to be equal to FRE. Okay, yeah, and then continue. Okay, continue. Yes. So now we have the circuit, right? Here we have ER. Here we have RR, and we have, right? We have chase XR. This EIR, right? Yeah, this is rotor circuit. So for this circuit, we have ER now become EI0 because the rotors is locked. So we have ER is S times EI0 because S is 1, so this one becomes EI0. So XI is what? SI is omega LR. LR means self-inductance of the rotor, right? This is reactant, this is self-inductance. Okay, so omega here is omega RE because this is rotor, right? This is rotor, so we have rotor electrical frequency times LR. Okay, so omega RE means 2 by FRE LR, right? Okay, and you should remember if the rotors is locked, if the rotors is locked, we have FRE equal to H times FSE and SE1 equal to FSE. Okay, so we continue with this one. We have 2 by, you know, FSE Okay, yeah. And units FSE 2 by is XR0. XR0. So actually we have S here, right? S here. So we have SR0 and SRE SXR0 and S is 1. So you get equal to uh, you get this one to be equal to xi0. Okay, yeah. So uh, okay, so we have fse times lr, 2 by 2 by fse times lr is xi0, and as you rewrite here. Okay, yeah. So now this one becomes xi0, right? Is SER0 equal to ER0. So here equal to JX R0 times S. Okay, equal, but S is 1, so you get X JX R0. Okay, yeah. So now the rotor circuit becomes here ER0. This is RR. This one is JXR0. Okay, and this AIR. Okay, yeah, and then we can guess IR is what? So IR is AR divided by RR plus JXR in general, right? So now we have ER equal to S AI0 divided by RR plus JXR is S times XI0, right? XI0. And the rotors is rocket, so S is 1. This is 1. So you can get AI0 over RR plus JXI0. Okay, this one is the equation of this circuit. Okay, now we come back. Yeah, so I mentioned before, we have okay, we have FRA is FSA. Okay, yeah, and the ER is S times EI0. Okay, so XR is omega RE times LR we discussed before, and the omega RE is 2 by FRE. Okay, 2 by FRE, and FRE is S times FSE. Okay, yeah. So if we let 2 by FSE, LR is XI0, so you get XR is S times XI0. Okay, yeah. So continue. So if the rotor is rotating, what will happen? Okay. Now we come back with this one. The rotor is rotating. Okay. So the rotor is rotating. That means H different from what? Because IR different from 0, right? SE S sin minus SR over S sin. So SR different from 0, so N sin minus NR different from 0, right? So S different from 1. Okay, and NR less than N sin. So N sin minus NR should be higher than 0 and less than 1. Do you repeat to me, Thế Bá? Any questions? So far, any questions? Okay, yeah. So for according to this equation, right? So you can get this one. Okay, yeah. So sorry, this one is not This one is not 1. This one is what? This one is um, n ns. So sorry, this one is ns. Okay. So continue. So we have n sin minus nr divided by n sin divided by n sin, right? Because if nr is equal to n sin, you get 0, and if nr is 0, right, you get the n sin. Okay, so if we divide this by right, so if we divide this by n sin, you get 0 over n sin, and this one is n sin over n sin. Okay, so that what is this? This one is s, right? And this one is higher than 0 and less than or equal to 1. Okay, so now I demonstrate to you why we have this condition. Okay, yeah, so because we don't know how many nr is the variable, so we just make sure that s is higher than 1 and less than or equal to higher than or equal to 0 and less than or equal to 1. Okay, so now we just say er is times ei0 and xr is s times xi0. Okay, yeah, we cannot say any certain values of s because nr is variable, so s is variable. Okay, now we have equivalent circuit. So here we have er. Okay, er. So er now es ai0. We cannot know. We cannot know the certain values of s. So we just keep s times ai0. So here we have rr. Here we have j is xi0 times s, right? Times s. Okay. Yeah. Yes, we have this circuit. Okay. And this is IR. Yeah. So now I modify this circuit a little bit. So look at this is this equivalent circuit. If I apply circuit 2, right? We have IR E S, right? ER0 over RR plus J X XR0, right? Right? We apply circuit 2 for this circuit. Okay. So I modify a little bit. Here we have S. Okay. So if I have ER0, then RR divided by S plus J XR0. This is the same, you know. The same, you know. Because this is time S. Okay, with time S, that means we divide this by with time S in the numerator. Okay, so we divide this by S from the denominator. Okay, yeah. So for now we get RR over S plus J xi0. Okay, so now according to this equation, I modify the circuit. So now sorry, now we have the new circuit. Okay, we have here we have ER0, and now this ERR, and this one is J over S, right? This is J XR0, and this one is IR. Yeah, look, now we have this one is AI0. This is RR over S, and this one is XI0. Okay, and here is IR. So according to this equation, right, we have the circuits like this. We have ER0 RR over S, and this HJ is XI0. Okay, so now we have the observation. Observation. So if we consider locket rotors, and this one is rotating rotor, right? Case. Okay, so remember, for locket rotors and rotating rotor cases, we have the same AI0, right? We have the same AI0. Yeah, so the key difference is here, right? Here. So if SE is 1, okay, so if SE is 1, so this circuit become this circuit because RR over 1 is RR. Okay, so we have the observation. Okay, we have the common voltage EI0 here, right? This is EI0. This is I0. Okay, yeah. So the key difference is, so the key difference is RR over S. Okay, this one. Yeah. Now, we don't care about the operation mode of the rotors. Rotors is locked or rotor is rotating. We have the same voltage EI0. Okay, and EI0 is constant. EI0 is constant. Yeah. EI0 is constant. So we come back. Now we have this one. Okay. Yeah, as I mentioned before. Look, now if the rotor is rotating, we have ER ES times EI0 and JXR E JXI0 and this ER. Okay, so we modify a little bit right here. Now we have ER0 divided by RR over S plus JXI0. Okay, yeah. Now this circuit, you know, ER is SEI0, XI is SXI0, RR become this circuit, you know. Yeah, as I mentioned before. So this is rotating rotor case, but the voltage is also EI0 because we modify the rotor. Okay. Now the rotor's resistance must be divided by S, like this, you know. Any questions? Thế bá. Okay, so from now, if we would like to indicate the rotor circuit, we should use this one. You know, if the rotor is locked, S is 1. S is 1. Okay, if the rotor is rotating, S will be in the range of 0 and 1. S should be higher than or equal to 0 and less than or equal to 1. Okay. Now we have the other observation. Yeah, look at this one. We have IR is equal to the ratio of EI0 to RR over S plus JXI0. Right? Yeah, this is RR over S. This one is IR. This one is J's XI0. Okay, similar, right? So we have two main observation. The first one, the first one here. If S is very small, if S very small, okay, if S very small, that means N sin minus NR very small. So that means NR nearly equal to N sin, right? Right? Yeah. So for S very small, so RR over S very high because S very small. Okay. Yeah. And then RS over S very high. So RR over S is much higher than XI0. XI0. Okay. So now we have IR is approximately equal to ER0 over RR over S. We skip XI0 like this, like this. Okay. And then we modify. Okay. So now it's one equal to ER0 times S over RR over RR, right? RR divided by S. That's mean the time S. Okay. So we have the conclusion. So IR is directly proportional to S. Okay, in this case, if S very small, if S is small. You know, look, very low slips. The resistance terms R over S is much higher than XI0. Okay, so the rotor current very linearly with slip. Okay, now high slip. That means SE approach to 1. Okay, so we have RR over S approach to RR, right? Right? Because S is nearly 1, so RR over S is nearly RR. Okay, and then you know RR is smaller than XI0. Okay, so now IR becomes ER0 AI0 AI0 over JXI0 because RR is very small, so we skip RR, so become this one, okay. Yeah, so ER0 is constant, XI0 is constant, so now IR becomes uh, constant, remember that. Okay. Yeah, so we have two observations. S is very small or X is uh, approaching to 1. Okay, any questions? Thấy ba? Okay, so next. Now we have the relationships between IR and S, right? So we draw the curve. This is the curve. So we have the curve. This is IR, right? And this one is S. You know, S is 0 and S is 1. Yeah, because the minimum values of S is 0 and the maximum values of S is 1. Okay, so remember that. So S very small, so IR proportional to S. That means if S increase, IR increase. Okay, so if S is approach to 1, so IR constant. Okay, yeah. So to similar with this curve, we modify a little bit. Okay, here we say S. Here we say S. Sorry. Here we say NC. Okay, NC. So S is what? S is what? So S is 1. SA, sorry, SAN since minus NR over NC. Or S is 1 minus NR over NC, right? Right? Yeah, we have the formulas like this. So if NR is 0, that means SA 1. Okay, and we know NR different NC. Okay, so here we have here we have rotor speed is 0, right? This is 0. So here actually here we say n rotor, right? Here n rotor nr. So if nr is 0, that means s is 1. So here is s is 1. X is 1 will be here. Okay. So if nr equal to NC, nr equal to NC, right? So this one is 1, 1 minus 1 is 0, so S is 0. So if here is NC, that means S is 0. This is 0. Yeah, so now we have the curve. So if S increase, IR increase, so we start here, right? We stay here. So if S increase, IR increase, so I get this curve. Sorry, I get this curve. Okay. No. If SR increase, so IR increase. Yes. Okay. So if S is approaching to 1, so ER now becomes constant. Nearly constant, right? Yeah. Okay. So this is the curve of IR versus S, right? If S is 0 and S increase, IR increase, S increase, IR increase, right? This is IR, right? S increase, IR increase. Okay, so if S is approaching to 1, IR will be constant like this. Okay, yeah. So we divide this into two areas. So these areas, right, we have high slip, because S is approaching to 1, and this area we have low slip. Okay, yeah. So from this curve, this curve equal to or similar to this one, you know. Yes. Okay. And we know here s is 0 and here is s is 1. I mean this curve. Any questions? So up to now, you understand how to draw the curve of IR versus S. Or you can say IR versus NR. Okay, rotor current versus rotor speed. Any questions? Jungwon, any questions?
I have no questions.
Okay, so continue. So this slide just review, review some information. For example, we have slip speed. So slip speed is the difference between synchronous speed and rotor speed. Okay. Yeah. So we can use rotor speed NR or NM or N rotor the same. Okay. Yeah. That is slip speed. This is synchronous speed, and this one is mechanical speed or rotor speed. We can calculate S. Okay, S. Yeah, of course. S E N sin over N R over N sin, or S E omega sin over omega R divided by omega sin. The same, the same here. And rotor speed is 1 minus f times synchronous speed, and omega m is 1 minus f totally times omega 6, the same, and the same meaning. Okay, so now we think about how to combine stator circuit and rotor circuit in the same in the unique circuit. Okay, so we have the transformer theory. Okay, for transformer theory, we need to refer all parameters from the rotor winding back to the stator winding. Okay, so for the rotor windings, we have sorry for the um, yeah, for the transformer, we refer on secondary winding back to the primary winding. So for induction motor, we need to refer on uh, rotor parameters back to the stator side. Okay, yeah. So for the transformers, we have VS, the secondary, right? VS, IS, ZS. This is secondary voltage, secondary current, secondary impedance. So for the primary side, we have VB, primary voltage, primary current, and primary impedance. Okay, so how can we refer? Okay, so we let we let vs we let okay, so we let vp e a times vs. What does this mean? A is the transformer ratio. Okay, A is the transformer ratio. So A is this transformer ratio. That means NS over NB. Sorry, NB over NS. Sorry. This A is the turn ratios of the transformer, so equal to NB over NS. So for IB, so IB is IS over A, and ZB is the ZS times A square. Okay, yeah, so we studied before from transformer theory. So A times Vs, we say Vs over comma. Is over A, we say Is over comma. And Zs times A square equal to Zs over comma. Over comma mean we refer on secondary parameter back to the primary side. Okay, so we have over comma here. Hey, sorry, over comma here. Yes, over comma. And remember that I the turn ratios of the transformers. Okay. Yes. So now we apply the same thing to these induction motors. Okay. So for the induction motors, we also have a effect. That means the effective turn ratio of induction motor. So for induction motors, we have N1. N1 means the number of turns of stator. We have N2. This is the number of turns of rotors. So we have the ratio, effective turn ratio of induction motor E N1 over N2. Okay, so for the rotors, we have what? For the rotors we have I mean we have the rotor parameters, right? We have IR, right? We have IR, we have ER, EI0, right? EI0, and we have RR over S. We have XR 0, SI 0. Yeah, right? If we look back here, for the rotor circuit, we have RR0, IR, XI0, and RR over S. Okay, we have 4 parameters. So now, IR, EI0, RR over S, and XI0, or we have ZR if you want. ZR means the rotor impedance. So ZR is RR over S plus J XI0, right? So we need to refer on rotor parameter back to the stator winding. Okay, so now we have IR time what? Divided by A effect. Look. and we define this ratio equal to I2. So what does this mean I2? I2 is the rotor current referring to this data. Okay, so EI0 now, if you refer EI0 back to the stator side, we have ER0 times A effect. Look. And we say ER overcomers. Yeah, I mentioned to use overcomers meaning, right? So the meaning of overcomers E the rotor parameter referring to the stator we have overcomer. So R over S. So you get R over S times A effect square, right? Similar with this one. And Xi0 now becomes Xi0 times A effect square. Okay, so ZR times A effect, the same, you know, A effect squares equal to what? Equal to RR over equal to A. Sorry, I erase on the ink slide. Oh my god. Okay. So how can I back? Maybe no. Okay, maybe no. So you should take into account my lectures. Otherwise, yeah, I deleted. Yeah, sorry, because I click here. Okay, yeah, no problem. Okay, so now for eyes, now we when we refer all rotor parameters back to the stator, yeah, we have look EI0 times A effect, you get AR over comma, and we define this one the I2, Z2, R2, X2. Okay, or we say I2 overcomers. Okay, Z2 overcomers, R2 overcomers, and X2 overcomers for easy, right? Yeah. So remember that these strips R or 2 mean rotor parameters. Okay. Yeah. So for synchronization, normally we use I2 overcomers, Z2 overcomers, R2 overcomer, and X2 overcomer. So now I summary for you. So if we have RR, XR0, IR, and EI0, also ZR. So when we refer all parameter here back to the status, we have Z2 overcomers, R2 overcomers, X2 overcomers, I2 overcomer, and what? ER overcomer or E2 overcomer. Okay, for easy to remember. Any questions? Okay, so and of course we have Z2 overcomers E, R2 overcomer plus change X2 overcomer, and R2 overcomer is what? R2 overcomer is ARR times A square, A effect squares, right? X2 overcomer is XI0 J's XI0 times A effect squares. Okay, anyway, we need to refer all rotor parameter back to this data. Why did? Okay, and we use overcomer. Overcomer mean refer it to the stator side. Okay, yes. So for now we can combine, you know. Yeah. So for yeah, so at the beginning we have this one is ei0, right? And this one is rr over s. This one is xr0. Yes. Okay, and this one is ir. Okay. So when we refer all parameter back to stator side, okay, you can get what? Now here is e2 over comma, and e2 over comma is what? ei0 time a effect. Okay, and yeah, similarly we have here is x2 over comma. Sorry. Hey, again. Okay, this one is R2 over commas. This one is J is X2 over comma over S. Remember over S. Over S. Over S. Yeah, over S. Okay. Yeah. And now we get I2 over comma. So if we already refer all rotor parameter back to this data, okay, now we have the same voltage with E1. So we can combine. Okay, we can combine this is rotor side. Okay, yeah, and this is stator side. We can combine rotor circuits and stator circuits in the same equivalent circuit. Okay, and I mentioned before, normally this one should be I2 over commas, X2 over commas. Okay, R2 over comma, and of course E1 equal to E2 over comma. Okay, so this is the equivalent circuit, the final equivalent circuits of induction motors. Okay, yeah, here, normally we use I2 over comma, R2 over commas, X2 over comma, and uh, okay, let us, I will explain to you why we get this one. So now, if we have R2 over comma over S, that's okay. Okay, RC, XM, IM, and this one is rotor, this is stator side, this is rotor side, and we combine them into the same equivalent circuit. Okay, yeah, any questions? Thầy bá. Okay, so I summarize for you before we take break. Okay, so look, now we have stator, right? We have R1, JX1, right? And we have a magnetic circuit. We have RC, JXM. Yes, this one is I1 over comma. I1 over dot, because this one is complex numbers, and the voltage here is V1 or V phase. Okay, yeah, and now we have internal voltage E1. Okay, so for the rotor circuit, we have here ER0, right? This one is RR over S. This one is JXR0. Yes, like this. Okay. And this one is IR. Now, we would like to combine. Okay, we would like to combine stator circuit and rotor circuit in the same circuit. Okay, in the unit circuit. So we need to refer, right? You need to refer on rotor parameters. Okay, back to the stator side. Okay, side. So now we need to consider A effect, right? A effects E N1 over N2, the number of turns at the stator over the number of turns at the rotors. Okay, so now this one become EI0 times A effect, okay, equal to E to over comma, right? Now we have RR over S should time A effect square. So this one equal to R2 over comma, okay? And we have here JXR0 times A effect square. So this one equal to X2 over comma, okay? Yeah, and now we connect with this one. Okay, so how about current? Current we have IR, right, divided by A effect. A effect, this one equal to I2 over comma. So now, so when we refer E1 equal to E2 over comma, right? So the same voltage. So we can connect here to be here and here to be here. Okay, because we have the same voltage. So now I redraw the circuit. Okay, now we have R1 JX1, we have RC JXM, right? This is V1 over to equal to V phase. Okay, so this is the same voltage, so we can ignore this one because we have no current. Yeah, okay, so the same voltage. So here we can get, of course, this one is E1 equal to E2 over comma. So here we have R2 over commas over S X2 over comma, right? And here I2 over comma. And of course we know what? We know R2 over S. R2 over commas over S equal to what? Equal to RR over S times A effect square. Yeah. And here JX2 over comma equal to JXR times A effect. A XI0, right? A effect square. Here. And I2 over comma equal to IR divided by A effect. Here. Okay. And you know E2 over comma ER0 times A effect. Okay. So finally we get we get the equivalent circuit of induction motors, okay, with the unique circuit. Okay, so remember that you need to refer on parameters of the rotors back to the stator side. Okay, finish. Yeah, so now so up to now we understand how to draw the equivalent circuit, the final equivalent circuit of induction motors. So now we take a break, 10 minutes.